Good, it works. Okay. Today, it's all about tangent. So we've done everything we need to do with sine and cosine. You need to know how sine and cosine work in order to work tangent. Okay? So today we're going to talk about tangent. We first introduced tangent of an angle in 3.2. So we just basically talked about tangent. At some point, we'll talk about cosecant, cosecant, secant, and cotangent, but not today. Today's just tangent. We define the tangent of an angle as the slope of the terminal ray as a ratio of angle. Tangent is sine over cosine. And if you know that tangent sine over cosine, opposite is always y. Opposite is always y. Adjacent is always x. Sine is y. Cosine is x. However, you got to remember that tangent sine over cosine. And if you know that, I think you're pretty good. I don't know tangent to this day, but I know that tangent sine over cosine. And so as I'm going through this lesson today, that's what I'll be just asking you questions about. Okay, so what's sine and what's cosine? Because if you know what sine is and you know what cosine is, then we know what a fraction is and we got a fraction. Here we go. I don't know why they have m. Y over x is the same thing as sine over cosine. So y is the opposite side, x is the adjacent side, and you know that tangent is opposite over adjacent. As we did previously with sine and cosine, we can use our understanding of the tangent function to develop its graph. Let's look at the slope of the terminal ray as angle increases from 0 to pi over 2. So we're going to be talking about the graph of tangent, okay? So before we talk about it through the notes here, let me just ask you guys some general questions, right? We know the graph of sine and we know the graph of cosine, or I hope you do, right? Sine and cosine are by far the most used trigonomic graphs, by far. It's not even close. Tangent is used ever so slightly. Well, if you know that tangent sine over cosine, and you know what happens to sine at certain points, and you know what happens at cosine at certain points, then you know what tangent is. For instance, pi over 4. Pi over 4. You should know what sine of pi over 4 is, and you should know what cosine of pi over 4 is. And that's the one where they're both square root of 2 over 2. And so if you have the square root of 2 over 2 and the square root of 2 over 2, and those are over each other, then you know that that value is 1. And so tangent of pi over 4 is simply 1. Good enough with that, right? So right here, where they're talking about this p-value, tangent is 1. Tangent is 1 at that particular point. That's the 45 degrees or the pi over 4. When it's right here on the x-axis, which is the 0 degrees or 0 radians. Well, that's where you got to think, okay, well, at 0, sine is 0, cosine is 1. At 0, sine is 0, cosine is 1. And 0 over anything is 0. So sine of 0 is 0. Tangent of 0 is 0. So tangent starts at 0. Tangent starts at 0. And then when we get to pi over 4, we're at 1. We're at 1. Let's go all the way out to pi over 2. Pi over 2. Sine over cosine. At pi over 2, straight up in the air, that's where sine is 1. But cosine is 0. And now we have sine over cosine, or 1 over 0. And your whole mathematical career, we know what about 0 in the denominator? That's bad. That's undefined. It's undefined. So tangent at pi over 2 is undefined because cosine is 0 at pi over 2 and tangent's sine over cosine. Kind of okay with all that stuff? Again, when theta is 0, the slope of the terminal ray is 0. As 0 increases, the slope also increases as it approaches pi over 2. The slope gets steeper and steeper and steeper and more positive. And the reason for that is sine starts off at 0, but sine is going up to 1. So sine starts off at 0 and sine gets bigger until we get to 1. Sine is getting bigger, so my numerator is getting bigger. But my denominator starts off at 1. But it's going to 0, so my denominator is getting smaller. Y'all with me on all that, right? So the numerator is getting bigger. The denominator is getting smaller. And as this number is getting bigger and this number is getting smaller, then that makes this number over here become bigger. Because as the denominator gets smaller and the numerator gets bigger, then it becomes a bigger number. So all that to say this. Here we go here. Well, when theta is pi over 2, the slope of a vertical line is undefined. Wow, this is really going slow today. It's undefined. And we can now see that when we say a slope is undefined, it's because it's infinite. And so look at this notation here. This is coming back into play from Unit 1. The limit as theta is approaching pi over 2 from the negative side. Approaching pi over 2 from the left side or the negative side. Tangent's going up to infinity because the numerator is getting bigger and the denominator is getting smaller. Now let's investigate what happens from pi over 2 to pi. Well, pi over 2 to pi is where sine is now getting smaller again, and cosine is sine is getting smaller because it's going from 1 to 0, but cosine is going from 0 to 1. And so therefore now from pi over 2 to pi, we're getting smaller. Smaller and smaller and smaller and smaller and smaller until we get to pi. Okay? And when we get to pi, that's where we have 0 over anything. 0 over 1. Okay? All right. All that to hopefully just give you a couple of aha moments. I look at tangent at 3 major points per se. Of course, it repeats. But I look at tangent at when it hits the x-axis, when it's 0. I look at tangent when it's 1, when sine and cosine are the same thing, which happens at the 45s or the pi over 4s. And then I look at infinities or undefines. Undefines. So I look at 0s, 1s, and undefines. Y'all okay with that? Sine and cosine, I just look at 1s, 0s, negative 1s. I don't care about all that, the pi over 2s and the 3 pi over 2s and the 1/2. I don't care about that for sine over cosines. I look at 1s, 0s, and negative 1s. Tangents, I look at 0s, 1s, and infinities or undefines. Okay? So if you guys can somewhat remember that, we'll be pretty good here. As we continue from pi to 3 pi over 2, we can now see it's positive again, progressing from 0, yada, 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 yada. So this is going through basically all 4 quadrants. Quadrant 1, quadrant 2, this is quadrant 3, and they didn't even do quadrant 4 because I think we kind of get the idea now. Key concept, each time a terminal ray is vertical, the slopes are undefined. They approach infinity or negative infinity. When the graph of the tangent function, this means we will see vertical asymptotes. And there is no way. Oh, there it is. It's right below it. Thank goodness. Thank goodness. Can't spell asymptotes. A-S-Y-M-P. I throw a P in there. Asymptote. Okay. This is what tangent looks like. That's what tangent looks like. Again, I'm going to focus on three major points: asymptotes, zeros, and ones. Negative ones. Ones and negative ones. Okay? So at zero, this is probably the biggest thing you need to know. At zero, tangent is zero. At zero, tangent is zero, because tangent sine over cosine, and at zero, sine is zero. And so I really don't care what cosine is, because zero over anything is zero. So at zero, tangent is zero. And the next time tangent is zero is when sine is zero. And sine is zero at pi. Then tangent is zero at 2 pi, 3 pi, 4 pi, 5 pi, negative pi, negative 2 pi. So tangent is zero when sine is zero. Yeah, oh, that makes sense. Tangent sine over cosine. If sine's zero, then tangent has to be zero. Okay? Now, 45s or the power of 4s. Pi over 4, pi over 4. That's when sine and cosine are the exact same thing. Sine and cosine are the same thing, and so that's why it's a 1 right there at pi over 4. It's a 1 at pi over 4. And then at pi over 2 is where we have an asymptote. Pi over 2 is where we have an asymptote, because that's sine over cosine, and at pi over 2, cosine is 0. If cosine's 0, that's bad. And so tangent has asymptotes when cosine is 0. A-S-Y-M-P-T. When cosine equals 0. Asymptotes when cosine equals 0. Intercepts, how about that? When sine equals 0. And then basically you got to know your positive and your negatives. Asymptotes when cosine equals 0, because it's sine over cosine. Intercepts when sine equals 0. And if you just kind of, like I said, you already know this part, and you already know when this happens. And so when those happen, you should know when tangent happens. Okay? Intercepts, intercepts, intercepts. Asymptotes, asymptotes, asymptotes. And then ones and negative ones. Okay, quadrant 1, it's positive 1. Quadrant 2, it's negative 1. Quadrant 3, it's 1, because that's where sine and cosine are both negative. So quadrant 1, here, let's go back up. I'll go back up for this. Again, you got to understand positives and negatives, right? Quadrant 1, tangent is positive, because sine and cosine are both positive. In quadrant 2, tangent is negative. Sine is positive, but cosine is negative. Positive over negative is a negative. In quadrant 3, tangent goes back to positive because both sine and cosine are negative, and a negative over a negative is a positive. And in quadrant 4, we're back to a negative. Okay? Always just keep that in perspective. Keep that in your heads. If you know what sine and cosine are, you should know what tangent is. If you know what sine and cosine are, you should know what tangent is. Quadrant 1, positive. Quadrant 2, negative. Then we hit 0, and now we're in quadrant 3, positive again, till we get our asymptote, and our asymptote's right underneath us. Sine is -1, cosine 0. Quadrant 4, we're at negative again. Okay? Important features of the graphs of tangents. Okay, so here's a couple of the big things about this, and again, you should somewhat be able to understand all this stuff. They're going to put the A in there again, they're going to put the B in there, they're going to put C, and they're going to put D. Okay? On the test, that messed some of you guys up because they ended up putting a C right here. They can put whatever they want. You guys just need to know that number over there all by itself moves things up and down. The number with the theta moves it left or right, or changes the period, and the number out front stretches or shrinks. A and D are Y's, B and C are X's. B and C are opposite of what you think. Vertical dilation by a factor of A. You really can't notice vertical dilations with tangents, because if you shrink infinity, it's still infinity. If you shrink infinity, it's still infinity. If you shrink a 0, it's still 0. So vertical dilations, you really don't notice. You would notice it at 1, at pi over 4. That's where you would notice it, where the stretch and the shrink would happen. Okay? Just kind of go along with me. You won't notice at the infinities, you won't notice at 0, but if you're stretching something up, you'll notice it at the 1s. Because you can stretch or shrink that. 0s, you can't stretch or shrink. Infinities, you can't stretch or shrink. But in between it, you can. All right? The period of tangent is pi. The period of tangent is pi. Sine, cosine, or 2 pi. Because it takes all the way around to repeat itself. Tangent starts repeating itself in quadrant 3. Bless you. Bless you. Okay? Because quadrant 3 and quadrant 1 are the exact same thing because they're both negatives. So the period of the period of tangent is just pi. Of course, C is still my horizontal shift, and D is my vertical shift, and I don't notice much about vertical shift, and I do a little bit. Where the 0s are, it's where my vertical. Okay? All right. All that to be said. All that to be said. Okay? Hopefully we took all that in. Example number 1. Example number 1. A portion of the function of f is shown above. The function of f can be written as a tan bx plus d. So we have no shift horizontally. Where a, b, and d are constants, find the values of a, b, and d. Find the values of a, b, and d. Okay? So d is basically how much that thing is going up and down. Okay? It's hard to tell where it's going up and down other than where you basically look at that, I don't know what you want to call it, that inflection point. Concave down, concave up. That inflection point. How about that? Concave down, concave up. There's the inflection point. And that inflection point is at 0. And because it's at 0, this thing is not shifted up or down. It's not up or down. So D has to be 0. D has to be 0 because, again, that's the inflection point. That's where that thing is going to change from concave up, concave down, or concave down to concave up. Okay? D. That's always the easy one. A is not as easy this time. A is easy last time because that was your maxes and your mins. Tangents don't have maxes or mins. Tangent doesn't have maxes or mins because of infinities. Let's look at B, the period. B, the period. We know that the period is equal to pi over B. Or we know that B is equal to pi over the period. Either one of those two formulas work. Those still the same thing. The only difference is now we have pi as opposed to 2 pi. So I'm looking for the B value, and the period, let's see, this goes from 0, and now that's pi over 4. That's pi over 4. Normally the asymptote's supposed to be at pi over 2. Normally the asymptote's supposed to be pi over 2. This one's pi over 4. So this one's going, when I get to pi over 2, let me rephrase that. The asymptote's supposed to be, okay, periods where it repeats itself. Let's do it this way, right? It starts repeating itself there. So this period is pi over 2. This period is pi over 2. It's probably a lot easier to do that instead of trying to figure out where the asymptotes are. So look at that point of inflection, look at the next point of inflection, and that's where it starts repeating. That's where it starts repeating. So this period is pi over 2. So if I do B is equal to pi over 2, and I do my flipping and my multiplying, I'm going to get 2 pi over pi, and so B is equal to 2. Pi over 1 over pi over 2. Whatever you got to do. The 2 goes up here, the pi goes down here, the pi's cancel. I don't know. 2. Yes, sir.
Why is it 2 pi? Or is it pi first, 2 pi first, sine and cosine?
Because it repeats in the third coordinate. Because sine and cosine are the same in the third quadrants as it is the first. Okay. I don't know how you want to do this. B is 2. That means it's going twice as fast. It's going twice as fast. I don't know. Normally my 1 is at pi over 4. That's the way I'm going to do it. I think it's the easiest way. I think. Normally my 1 is at pi over 4. How about that? Let's do that. This may take questions for you guys on Wednesday. Normally, pi over 4 is my 1, because that's where sine and cosine are the same thing. But this one's going twice as fast. So pi over 8 is where my new 1 is. It was pi over 4 is where 1 should be, but this one's going twice as fast, so now it's pi over 8. And if I go to pi over 8, which is halfway between pi over 4, I better be at 1, and I am. That one's really hard to do. It's going to take you guys questions on Wednesday for me to realize how you guys are thinking on what that, and it may be easier than I'm thinking it is. Oh, yeah. Yeah. Yep. Well, So her question was, is A different than the amplitude? Is that tangent doesn't have an amplitude officially. Amplitude's how far the maxes and the mins go, and these don't have maxes and mins. Well, I'm trying to explain how I got one. Dax, how do I get one? Can somebody tell me how I got one? So I'm trying to figure out how you guys think. You don't know, have a clue how I got one?
No.
Cuss.
Take the value, you get 0, start the between the concave up and concave down,
You're on the right track. Hit me. I'm trying not to do this algebraically for you guys. I'm trying not to, but it looks like I'm going to have to.
Found where pi over 4 was on like the original tan graph.
Yes.
Like horizontally shrank it. Then you found out where pi over 4 was on the new one, pi over 8. Then you compare the two values you get.
That's how I did it. But that's probably not how you're going to do it, huh? All right, dang it. I'm making this a whole lot harder, and it's really not that hard, but I'm doing a -3 job of explaining it. Okay, let's talk about the parent function of tangent. Talk about the parent function of tangent. Okay, like what tangent's supposed to look like. Let's go from there. Come on. There you are. Good gracious, that took forever. Okay, so tangent. Whoops, I still got to wait. Still too long. Oh, there it goes. Tangent. So that's the y-axis. Here's the x-axis. At 0, tangent is 0. At pi over 2 is my vertical asymptote. That has to mean, or I hope it means, hope you realize that it means at pi over 4, exactly halfway between that, that's when we are 1. Pi over 4 is halfway to pi over 2. 1/4 and another 1/4 is 1/2. Okay, so that's where we're 1. And so this thing looks like that on that part of it. Okay, negative pi over 2 is my next vertical asymptote. And here at negative pi over 4, that's where I'm at -1. And there's the other part of it. And so that's 1 period, which is a little different because we're not used to seeing negatives as part of the period. If you want to see the other part of the period, it becomes a little weird, right? This is 1/4, this is 2/4, here's 3/4, which I'm back at -1. And then at 4/4, that's where I'm back at 0. Okay, so here's my -1, here I'm back at 0. So that's also a period. That part of it and that part of it, right? We got a period. Okay, so the graph that we were just doing is going twice as fast because the asymptote was not at pi over 2, it was at pi over 4. That's where the asymptote is. Okay, so it's shrinking everything down. So at pi over 4 is my asymptote. So at pi over 8 is where I should be at 1. And I am. So because I am, maybe I'll just set up an equation. Okay. Y'all just go with me on this one. That one's 1. It's 1. Plug and chug if you have to. Plug and chug. Any graph you can always plug and chug. When I get to pi over 2, go ahead. Knucklehead. You're a doofus. I get paid to do this. I don't even know where he was. What was he doing? Calculator. I don't know where he was. I know. I just don't know where you were. That's Jonah. No, don't do that. We're trying to figure out what A is. There you are. Ring, ring, ring. Reopen it? I can't reopen it. He closed it. You're a doofus. Yes. Man, I just can't fix some things. Calculator? Calculator. You're welcome. I love you. Good luck. All right. We're going to jump to example 2. Yeah.
Can you show us what A would be on like the regular tangent?
On a regular tangent, A regularly is 1.
So like without
A.
What is this?
It's the inflection point. No, 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 no. It's where it's 1. No.
Are you sure?
No, it's not always 1. On the parent function, A is 1. You with me on that? Go with parent function, A is 1. On the regular tangent, A is 1. Because there's no B. Well, B is 1, or B is pop. No, B is 1, and C is 0, and D is 0. So A is 1. What'd you do?
I don't have a non-calculator.
The non-calculator. I love this job. I love using computers. I should just give it to you on paper. Should just give it to you on paper. I'm an idiot. Here, let's just do it that way. Non-calculator. Would have made this a whole lot easier. There you go.
Thank you.
You're welcome. Yeah. A is where, I don't want to say A is there though, because A could be anywhere. I know what you're thinking. I know. I got you. Okay. What's A in this one? Pretty easy, yeah? Okay, let's see what happens. I'm trying to make this a whole lot harder than it is, but I'm doing a good job of that. Oh, all they want to know on this one's a period. So do I care about what A is? Okay. Do I care what C is? Do I care what D is? And I care what B is. Fair enough? Because we know the period is what? Pi over B. Right? We know that. And what is the B value on this one? 2. So the period of this one is pi over 2. Easy peasy lemon squeezy. Okay. Whoops. Okay. Easy there. Let's keep going. I'm way making this too hard. Let G be the function defined by that. Which of the following gives a vertical asymptotes? So in your mind, right now, or at least in mine, when I hear vertical asymptotes or tangent, I care when cosine is 0. Fair enough? I don't even think about tangent. I care when cosine is 0, because when cosine is 0, tangent's undefined. And when tangent's undefined, we got a vertical asymptote. Okay with all that? So I'm immediately thinking, okay, I care about when cosine is 0. And cosine is 0 when the duck is straight up in the air at pi over 2. Normally, right? This thing shifted. So pi over 2 is where this thing normally is at 0. That 1 does what to the whole graph? Moves it up 1. Down 1. Moves it down 1. So that's not going to affect that vertical asymptote. Move things up and down doesn't affect vertical asymptotes. Moving things left and right does. Shrinking them out and in does. So this has no effect on a vertical no effect on the vertical asymptote, or no effect when cosine is 0. This has no effect when cosine is 0, because cosine is 0 when this thing is shifted left, right, or shrunk and expanded. Dilated is all we use. And this thing's not shifted left or right. However, it is shrunk or expanded, or it is dilated, because it's going 1/3 as fast. So B is 1/3. So we know that the period is equal to pi over B, right? Period's equal to pi over B, and B is 1/3. B is 1/3, and when I flip and multiply pi over 1/3, I'm going to get the period to be 3 pi. The period is 3 pi. Normally tangent's pi, but I don't care about tangent. All I care about is cosine. All I care about is cosine. So when cosine is 0, normally happens at pi over 2. Normally happens at pi over 2. However, because my period is 3 pi, and it normally happens at pi over 2, I'm going 3 times as fast. How I had all this planned earlier is not working. I should have got here a whole lot earlier. Well, no, it's not going like I planned it. Everybody okay with the 2 and the 1 not making a heck of beans or anything about this? Good. We're at a good spot there. Okay, let's do it the easy way. Use the answers. Pi over 2. Good enough? Pi over 2. Pi over 2 over 3 ends up being 3 pi over 2. Pi over 2 over 3. No. Pi over 2 over 3 becomes pi over 6. Yay? That's still not going to help me any. The answer is C. What's the period? Y'all okay with a period being 3 pi? Which one of those up there has 3 pi? Okay. So now my problem is if there were 2 of those with 3 pi. Oh, they'll do that. Say again? Okay, so that we need, yeah, that's a good question. Okay, so y'all know it's a period, right? So it repeats itself a lot of times. Good enough, right? It repeats itself a lot, and so k is any integer, meaning 0, 1, 2, 3, 4, 5, 6, 7, -1, -2, -3, -4. So we don't know what k is, but it could be any integer because it repeats itself. It asks which of the following gives the vertical asymptotes. That's all of them. Well, the only way to list all vertical asymptotes is I've got to do that k thing, because k could be any integer, and I can't list them. It's impossible to list them all. You can't. It's like trying to find the x-intercepts for cosine. I can't list them all. It's like trying to find the x-intercepts for sine. I can't list them all. I can't, because it repeats itself to infinity and negative infinity, and you cannot list them all. So they will do that little k there to make me talk about it being, and k is any integer. Okay? So if k was 0, then 0 times 3 pi is 0, and therefore x would be 3 pi over 2. And I would put in 3 pi over 2 for x. If k was 4, 4 times 3 pi is 12 pi. And so I would do 12 pi plus 3 pi over 2. So it repeats itself so many times. Yay? Does that help you with k? Correct. Constant. Yeah. Oh. K is a constant. Yes. Your notes say what? It really does? All of yours say constant? Yep. I mean, yeah, constant. I don't know what the difference between a constant and an integer is, other than constant is. I'm assuming they were all integers because my teacher made me write integer. All of yours say integers, or all yours say constant? I think it's supposed to be integer, and I think they messed up, and I think this is supposed to be integer. They fixed 3 of them, and I don't think they fixed the answer. Huh. I'm glad you told me that. Let's keep going. Seriously, this is not hard, but boy, I sure am making it that way. Okay. Soak this up. A portion has been drawn. Y'all good enough with this just being a portion, yes? Because I can't draw the whole thing because it repeats. And I've drawn what? 3 periods. I've drawn 3, or I haven't. They did. They've drawn 3 periods with 1, 2, 3, 4 asymptotes. 1, 2, 3 intercepts. Yay? This graph has moved up, down, or it's or is at 0? How about that? Can everybody see that this thing has moved which way? Which way? Okay. Thank you. By far, this thing's moved down because that's the point of inflection. Okay? So the D value for this stupid one is -2. Okay? The D value is -2. how do I say? It is not shifted left or right. It is not shifted left or right because the point of inflection is at 0. Y'all okay with that? It could be shifted left or right, but if it's shifted left or right, it's shifted left or right pi. Because pi is the period. And so I could shift this thing left or right, just like sine, cosine, just like sine and cosine, I could shift that thing 2 pi. Because it repeats itself every 2 pi. So if it starts at 0, it could start at 2 pi. Or it could start at negative 2 pi. This thing could start at pi. I just messed up because I said that. But okay, so what was that number? That's C. We're good there, yes? Okay. A stretches it or shrinks it, and it's hard to see a stretch or a shrink. Okay, here's how my stupid mind works. Y'all good with that being the 0 and this being an asymptote, yes? Halfway between 0 and asymptote, I should be at 1. Halfway between 0 and an asymptote. And I don't care where the 0 is. I don't mean 0 as in because that's the y-axis. Wherever the inflection point is and the asymptote. The inflection point and the asymptote, halfway between that, I should be at 1. That's that A thing. Halfway between this and the asymptote, I should be at 1. Yay? That's the A value. That's 1. Can we go with it for that way? That's kind of the way I was doing it. I'm trying to keep you from doing algebra because algebra seems to be confusing. However, algebra is not confusing right now. What I'm telling you is confusing. The period for tangent is pi. This goes from here to here. That's the repeated times. Yes? You can look at asymptotes, or you can look at zeros, or you can look at the inflections, or you can look at wherever you want to. Wherever you want to start and wherever you want to end, wherever it repeats itself is the period. So I will go from here to here, which is 2 pi. Good? So the period for this graph is 2 pi. And we know that B is equal to pi over the period, which is 2 pi. I'm not going to flip and multiply that one. Therefore, B is 1/2. Because it's going half the speed of a regular one. Because by the time I got to 2 pi, I'm doing a whole period. Normally when I get to pi, I should have done a period. What's their question? Oh, which of the following could be the expression for K? It's darn sure not D, and it's darn sure not B. We have a choice of A or C. And because B is 1/2, I got to go with A. Good enough with all that? Luckily, they didn't put any A values in there. All the A's are 1. 8, I don't want to say it. Halfway between the inflection point and the asymptote, I should be at 1. Let's go back to that one that we had the big issue with. Is that this one? Yes. Halfway between the inflection point and the asymptote, I better be at 1. And if you are, then the A value is 1. That's the only place you can tell where A is changed. You can't tell it at asymptotes. You can't tell it because you're stretching it, and you can't stretch asymptotes. So the only way you're going to notice a stretch is between here and here. That's about the only place I can go to stretch it to even notice it. Y'all with me on that? A is hard to see. A is hard to see on these graphs. Just like quadratic, the difference between a quadratic and a quartic, they look the same, except from 0 to 1. A quartic is a little bit flatter, and after 1, it goes up faster. But it's hard to tell that on a graph. It's hard to tell A values on these graphs, because the only way you're going to notice it is between that stretch between the 1 and the -1, or the halfway points. I hope you know your unit circle. Told you guys at some point you've really got to know this unit circle. And this is where it comes into play again. Tangent of pi over 6. I don't have that memorized to this day. I cannot tell you what tangent of pi over 6 is. But I can tell you what sine of pi over 6 is. And I can tell you what cosine of pi over 6 is. And if I know what sine of pi over 6 is, and I know what cosine of pi over 6 is, I can do some flipping and some multiplying and to tell you what tangent of pi over 6 is. Fair enough? Pi over 6. I may have to draw it. I still have to draw these things. Pi over 6 is that really, really close one. That's the very first one. That's the very first one. And that's where sine is 1/2. And cosine is the long one, so that's the square root of 3 over 2. And we're in quadrant 1, so it's positive. And so I'm going to put 1/2 over the square root of 3 over 2. And flip and multiply. The 2 is going to go up there. The square root of 3 is going to go down there. And you're going to have 2 over 2 square roots of 3, which ends up just being 1 over the square root of 3. Which might be square root of 3 over 3. I don't know if they want you to rationalize the denominator or not. Y'all follow what I'm saying? There's a radical in the denominator, and normally you can't have radicals in the denominator, so you need to multiply it by the square root of 3 over the square root of 3. Multiply it by the square root of 3 over the square root of 3, that gives you the square root of 3 over 3. Same thing. I don't know what they'll want as the answer of that. Either one of those are acceptable right now. This one's easier than that one. But this one's not rationalized. So if it says rationalize it, you got to make it look like this. If it doesn't say rationalize it, I'm leaving it like that. Pi over 4. Pi over 4. That's in quadrant 1. That's where sine and cosine are the same thing. I do have this one memorized. But even if I don't have it memorized, I can think about it. Pi over 4 is square root of 2 over 2 over square root of 2 over 2, because sine of pi over 4 and cosine of pi over 4 is the same thing. And you put the same thing over the same thing, and you're going to get, are you good?
Yep.
Awesome. Thanks. Good enough of that? Pi over 3. Dadgummit. That's the one after this one. I may have to draw it. Pi over 3. That's where cosine's the short one and sine's the big one. And if sine's the big one, that means sine is the square root of 3 over 2. And cosine is 1/2. Well, this one's really nice because when I flip and multiply this one, that's the square root of 3. And you can't simplify that. No telling what that is. That's annoying. Wowzers. Does that bother y'all's ears real bad? Woo! That pitch right there has got mine going nuts. Wow. Wow. Can everybody hear that? Wow. Whatever that pitch is. Whoa, turn that off. It's in here. It's my what? It's in here.
Definitely to my right. Bring it to your camera.
No.
No, it's stupid. Why would
It's not my helmet. Woo! All right. 5 power 6, 5 power 6, 5 power 6, 1 6, 2 6, 3 6, 4 6, 5 6. Negative. It's negative. Because sine over cosine. Sine's positive, cosine's negative. Negative. Sine's a short, cosine's a long. Sine's a short, cosine's a long. So you're either going to have 1 over the square root of 3 or square root of 3 over 3. You'll start getting these down after you do it for so long. Okay? Negative though, that's where we mess up a lot of times. Quadrant 2, tangent's negative. 4 power 3. 1 6, 2 6, 3 6, 4 5 6 7 8. Positive. 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 Sine is the long. Cosine is the short. Positive. 7 power 4. 1 4 2 3 4 5 6 7 fourths. Tangent's negative. Tangent's negative. Negative 1. Negative 1. 3 pi over 2. 3 pi over 2. 1, 2, 3. Sine. Cosine is 0, undefined. Undefined. We just got to know these. And however you got to do to figure them out. Pi. That's over here. That's where sine is 0. I don't care what cosine is. I don't care what cosine is. Pi over 2. Straight up in the air. Sine is 1. Cosine is 0. Undefined.